So we'll be discussing about on a new topic, that is on artificial neural network. This is covered from these chapters. You will find this is discussed in these chapters of these three books. So what I am referring at, as you can see, pattern classification by Duda, Hart, and Stork, and then Alpedin's book, and also in Tom Mischel's book. Now, we have discussed about perceptron classifier, and there the concept was that in a perceptron it can be considered as a kind of functional block where it takes a input feature vector, and then the weighted combination of the corresponding components of that vector. In addition, there is a bias term. So if I consider that, that becomes the net input to a nonlinear function, what is also characterizing this particular functional block. And you can see the examples of different nonlinear functions that we have considered here. These are typical examples. The signum is nonlinear function is simply capturing the sign of your net input. If it is positive, the output would be 1, or if it is negative, the output would be -1, and 0. It is bit undefined. It could be 0 also, but it is undefined, usually 1 and -1. And then the other kind of nonlinear function, which is which has a property of continuity, as you can see, that signum is not a continuous function; it is discontinuous at the functional value 0. That's why there it is not it's not defined. But when you have this sigmoid function instead of signum, then the functional form is given here in this form, that is 1 by 1 plus e to the power minus z. And you can see that this function, as z tends to infinity, it will reach 1. Similarly, if z tends to minus infinity, then it will reach 0. So, but it varies continuously. That is the advantage of this function. And we call this function also logistic, and we discussed that this is the inverse of the logit function. There is another interpretation by which you can compute the posterior of a class. We discussed earlier these things. Now the thing is that this perceptron model can be used as a linear discriminant classifier if I use signum function that we discussed. And on the other hand, we can consider a very good analogy with the function of a neuron, the way it interacts in our cognition pathway or in our sensation pathway. So as if a neuron will have stimuli from different points, and they are connected to those corresponding input lines, input connections. Say this part, as if these are the stimuli points. These are the stimuli points, so they are representing the feature vectors, and those are exciting this particular neural cell. And there is a threshold above which, if this excitation goes, then it releases a pulse. So this is the kind of behavior of a neuron. You can read it in details in biology also, in cellular biology, cellular functions. And the interesting part is that this information, so this is carrying some information in this way, and this is again fed to another group of neurons, and in this way, in overall network, there is a kind of stimulation which is propagated through the network, and finally at some In the brain, if I consider there is some computational blocks, so in the brain, actually the final decisions, etc., is taken. We know that in the nervous systems, finally they are connected to our brain. So the fact is that this kind of structure, this kind of topology has excited the scientists who are modeling this decision-making task, and they considered a network of perceptrons. So perceptron has captures a behavior of the neuron in this way. As you can see, that nonlinear functions of function of the excitation, what the neuron is receives, that nonlinear function is expressed by these typical functions of signum or sigmoid, etc. And whereas this bias term is acting like a threshold in this case. If the innate input is greater than bias only, say for example, then it will be I mean the whole thing, if it is greater than 0, so you can find out what is the mathematical interpretations, then there will be an output. So the idea is that a network of perceptrons that provides a very powerful model to describe these input-output relations. So I'll be explaining it further, and that is how an artificial neural network concept has been developed. It's a network of perceptrons, and in the network, the input is a vector, as we have already identified there, whereas the output also could be a vector or a scalar. So typical example has been shown, and you can see that each circular node is representing a perceptron here, perceptron node here, and they are connected, they are interconnected, and one typical structure. So one of the topology which is of very wide interest, that is called feed-forward network. It means that all the connections in one direction. It's a kind of one-directional directed graph if we consider them as a node, and there is no cycle there within that graph. So there is no feedback or loop in the network. And in particular, you can also model this network, describe this network as a layered, multi-layered network where you can say the information is processed layer-wise from one layer to the another layer. So output of one layer is input to the another layer, and it's a cascade of these layers that would make the network. So here an example has been shown, and there are certain terms that is used with respect to the description of this network. We will stick to those terms. You should also understand their definition. First thing is that now the input is given to the first layer. If I say, it can be directly connected to the layer which is producing output, or there could be in between there could be cascades of layers, and these layers are called hidden layers, in fact. So it has output, as I mentioned. So as you can see in this connection, so the first hidden layer, then the second hidden layer, and then you have output layer, and which is providing also the output. So sometimes the term input layer is also used to denote that the input that itself is the input points, input data points, stimulation points, to say. Now, so in this computational model, it's a layer-wise processing, as I mentioned, and the ith layer takes input from I-1th layer and forwards its output to the input of next layer. So that is the way it computes, and we call it fully connected feed-forward network. Fully connected in the sense you can see that for a layer, let me explain this term. So you take any particular node in the I-1th layer, so it will be fully connected to all other nodes of the ith layer. So that means there is no, there is no sparsity in these connections. So from this layer to this layer, every node of this layer is connected to every node of this layer. So that is meant by this kind of fully connected kind of definition. So we can also describe in a mathematical form this particular layered architecture, and we can say that there is a ith layer and a neuron in the ith layer. We can use another index j to denote that neuron. So it's a jth neuron of ith layer, and we denote it by this particular symbol as it is shown here, that no, it is this symbol. Any then subscript is used for denoting the jth neuron, and the superscript is used for denoting the layer. And it will also have its corresponding set of weights which are connected to the neurons of the next layer, which means that I can denote that set of weights, as you can see that for the ith neuron, you have jth neuron. Oh, sorry, this neuron is connected from the I-1th layer by this no, by different set of inputs. So these are the input weights connected to this neuron. Right. So to describe a particular perceptron, you require to know what is the connection of weights from its inputs. So this weight vector for this neuron, it is denoting the connections from the neurons of its previous layer, and that is why, according to our notation, you can see that I have kept this as j. This is a kind of subscript. So this j is the jth neuron of the ith layer, but this is the first neuron of the I-1th layer, second neuron of the I-1th layer, and the total number of neurons in a layer, if I denote it by ni, it is n-1th neuron of the I-1th layer. So that is the last neuron, if I say in our order. And for every neuron will also have a bias. So we denote this bias as wj0i. And this is the dimension of input to the neuron. As you can see, that because the input is coming from the previous layer, so the number of nodes in the previous layer is ni-1. So naturally, the input dimension is n-i-1. Similarly, dimension of output at ith layer would be ni as per our notation. So these are all notations. So I'm consistent with my subscript notation. So I'm just explaining them. And so output of the neuron can be then expressed in this mathematical form. This function is also denoting an operations over the pointwise operations of each element of the matrix. So you can see it is a matrix notation, and the definition here is that this is the corresponding input feature vector from the I-1th layer to ith layer, and this is the matrix denoting each row denotes the corresponding weight vector, right? So the weighted combination of input feature vector at each neuron, each jth neuron, will, this is the net weight at the j plus the bias. It is the net weight, and then if you use the nonlinear function, that would give you the corresponding. So it is not matrix, it is the wji. So it is a row vector. So it is a column vector, it is a row vector, right? So what is the dimension? Can you tell me what is the dimension of this feature vector as per our notation? This is the dimension of the input to the jth neuron of the previous. So the input is coming from the previous layer. So as you have seen, that dimension is ni-1, right? So I can write this dimension as, according to my notation, ni-1. See, I would have comfortably written subscript, but the problem, there is some limitations in using this composition. So ni-1 cross 1. So this is the dimension. And similarly, Wji, you can see this is a row vector, right? Wji transpose, it is basically the row vector. So it is 1 cross 1 cross n I j minus 1 plus Wji naught. So this would give you the net output, net input to the perceptron node, which is the jth neuron rather, and then use a nonlinear function to get the corresponding. So that it is described, functional description. So I can write in this form for a particular output of a jth neuron, I can write in this form. So the input-output relation in the ith layer, which means you have a set of such neurons at the ith layer. For each one, you need to describe it, and there I am taking this particular representation where I am using the vectorial representation of the output from the ith layer, which is first it is denoting the net input to every neuron of the ith layer. So you can see here, as per my notation, once again, see each row, it represents a particular weight vector connected to that particular neuron. So this is for the first neuron, this is for the second neuron. These are the weight vectors connected to those neurons. And your input is always the same, which is coming from the previous layer. Of the dimension, as I mentioned, it should be, as per my definition, it is ni minus 1. So dimensions need to be consistent when you perform this operation. And then, of course, for each one, there is a bias. For each neuron, there is a bias, different bias. So they are not the same. There is a different bias, and that is what is used, right? So since there are ni neuron in the ith layer, so you have so many weight vectors. So what is the dimension of this matrix? Can anyone tell what are the dimensions? So if I look at the dimensions, we'll be able to understand. Since what is the dimension of this? Let us understand that. That means this is the dimension of the net input. So you have these neurons, right? You have these neurons in the ith layer. So how many neurons are there? As per my notation, it is ni neuron. I'll be using simple subscript. I'm not using dash. Say ni neuron. So the dimension here would be ni cross 1. Okay, this should be ni cross 1. Okay, and each one will have input from the outputs of the previous layer. So this, how many nodes should be there? It is ni minus 1, right? Ni minus 1 should be that is the number of inputs. So you will find that the dimension of this one, it is the same input actually. So dimension of this one would be ni minus 1 cross 1. Okay, I minus 1 is the subscript, and the dimension of this one would be ni cross ni minus 1, because you have ni number of weight vectors, each of ni minus 1 dimensions. Each row is of ni minus 1 dimension. And naturally, this will be also ni cross 1. So this is how this dimensional matching can also, consistency can also make these things clear, that how net inputs of this layer are represented. So this is a vector which is representing net inputs. Net inputs means at this stage. After that, the output is there, which means if I apply nonlinearity on the net input at this point, then only I am getting output, which I'll be once again showing in a composite form. So I am representing this particular set of weight vectors by this Wi, that is the weight matrix for the ith layer. Similarly, this is the bias column vector of the ith layer. And you can see that the whole representation is explained here, which means I have the corresponding, say this is the output vector at the ith layer. This is the output vector at the ith layer, because I have used this nonlinear function. So this is a kind of composite representation, which means it will it is acting over a vector, over a column vector, and in a pointwise operations of the field of each column vector, and it is also providing you the same dimensional column vector. So finally, as you can see that to a simplified representation of this computational model, each layer is represented by a set of weight vectors and also a set of biases, like weight matrix. If I say weight matrix and set of and a bias column vector, each layer will have these things. So these are the parameters of the network, and this is how the computation is carried out in cascaded stages. And you have an input vector, feature vector or input vector, and you have an output vector. So this is in brief, this is the mathematical description of the computation what is carried out in the artificial neural network model. Right. So this summarizes the thing. Finally, on the onset, I mean, from the surface, we can say that this is a computational block, and which has a set of parameters. The whole set of parameters is W. Okay, and this is a computational block. So whole thing, as if it's a system that is artificial neural network system, and it has these parameters, and there is an input to that system, and there is an output to that system. Is there any question? So you can see what are the parameters here. Okay. Any query or any questions on the? And you can also count the number of parameters individually. You can count the number of parameters. These are the parameters. So each layer, from each layer, you will get the count, how many weights are there, how many biases are there, and simply you go on adding them, and that would give you the total number of parameters of the network. So now a artificial neural network modeling can be also considered as a kind of a modeling input-output modeling of the input-output description. I mean, it can be considered as a regression problem. Also, you can turn it into a classification problem. Primarily, I can say it is like a regression problem. So you are trying to best fit the model so that given input, you should get the corresponding desired output. So this is the problem. So if I give you a labeled set of data, labeled, or I should say this information about the specification, input-output specification of the data, where xi and y is given, and we have to find out w such that it produces y. And naturally, it's the mean square error. Mostly that is what is considered, but there are other forms of loss function which is also used in other contexts. But we'll be discussing only this particular type of optimization with respect to this artificial neural network. And here we are trying to match the output given an input as close as possible. We have to predict output as close as possible. So we will be using that same mean squared error, and we would like to minimize. And naturally, if the W is the set of parameters, and then this problem is this. And once again, you can apply the gradient descent procedure to obtain the same solution. Fine. So so this is the simple way of understanding the computations that is carried out over artificial neural network, and also the problem definition for training an artificial neural network or optimizing the parameters so that it matches input-output specification. So the method of gradient descent is the similar. You can start with initial W, and you can go on W iteratively, and you have to compute the gradient at that parameter point, and use this. You move towards the opposite directions of the gradient. So you can see here this particular notation. This is the gradient value, and as you can see, there is a negative sign. So since we are moving opposite, so it becomes positive, and this is the step size. This is the same, and here also you can see that now you are using the all samples of the training examples, but we can use the same relaxation approach where stochastic gradient descent approach where you can incrementally update the weights for every observations using using computing gradient for every observation separately or independently. So stochastic gradient descent will be given in this form that you have this weight updation, and you can see that this is the equation. So incidentally, I should point out, you can see the similarities also here, that while updating weights, this is a factor. That means you are considering the difference between the targeted value and predicted value, and then you are multiplying with the corresponding gradient value in the opposite direction. So that negation term is also included, and that's why it becomes simply positive. So let us now try to understand that the computation, how to compute the gradient of this network, gradient of this system, how to compute this gradient. If I consider a single neuron, and you can see that computation of a single neuron can be done very easily using analytical methods if I use chain rule. So let me first explain that what kind of options are with you for computing gradient. One option is that suppose your function is very complex. Now this function is not so complex. Suppose this function is very complex, and it is very difficult to perform analytical operations over that function. It may not be possible always to perform analytical operations over the functions to get a gradient function. So empirically, what you can do, you suppose this at some point you want to compute the gradient. So you give small perturbation on the sample values, that feature values, and you observe what is the change in your output. Okay, so you can, if it is a partial derivative, suppose you want to compute the gradient with respect to W2, give a small perturbation on W2 and find out what is the change in the output, and that change divided by the change of this W2 should give you an estimate of the gradient. Now that is an empirical method, but as you understand, it is very computationally intensive, because for every parameters, if you want to do it, then even it requires, it means it requires this forward computations. Of course, always you have to compute the functional values at those points, and you are doing it so many times, so it is very inefficient in that sense. But that is one way one can compute gradient empirically given any function. That is also always there. But the interesting part is that in training artificial neural network, we will not do that, because I told you that is inefficient. So what we will consider, we'll use an efficient method, and name of that method is called backpropagation algorithm. So I will discuss it. But before that, let me explain you that the principle behind computation of this gradient from the analytical point of view, from the, if I consider a single neuron, and we can see that that is used in backpropagation algorithm also. So this principle is that chain rule, that all we know from our school mathematics, chain rule of computing the gradient, or chain rule of doing differentiation of any function with respect to a set of variables. So you would like to apply that. So this is the thing we would like to compute, right? Gradient with respect to W means partial derivatives of the function. As you can see, in our case, we have taken the energy function as this is our, not energy, error, we call it error. So this is the error function, we take it. Usually there is a half factor to take care of these two. But here in my example, I'm just simply taking square of deviations from the target. It's a target value, target response. So T is a target response and O is your output. So the error of your computation with this, given this W is T minus O whole square. So now you have to compute the gradient with respect to W, means you have to compute delta E, delta W naught. So this parameter W naught. Also for each parameters in this input connections, you have to compute this partial derivative. So let us consider a particular parameter and see how this response could be, how this computation could be carried out using chain rule. As I see that E is a function of O, then O is a function of Z, and then Z is a function of Wi. If I consider this, then using chain rule, I can simply write in this form, that is delta, you can see here. So this is what we have written here, delta E, delta O, then delta O, delta Z, and delta Z, delta Wi. So individually, you can compute to this very easily. Also, delta E, delta O, what should be delta E, delta O? It should be twice T minus O, right? That is what is delta E, delta O. Sorry, minus 2 T minus O, because T minus O with negative sign. So it is minus 2 T minus O. Then delta O, delta Z, that depends upon the functional form. And you have to understand that even if the function is not continuous, it may be piecewise continuous, and at that value, it may be possible to compute the gradient. So it is not that if the function is non-differentiable, which means it is not differentiable at certain points, that this gradient is not computable. That is not true. Anyway, for a continuous function, we can always compute it also. Let me represent it as a prime Z, because the functional form may vary. We'll see a typical form if I take sigmoid function. And then we can take the gradient of the Z, partial derivative of Z with respect to Wi. And as you can see, Z is a linear combination of these inputs. So weight is the parameter here. So this is the expression for Z. So you get Xi, and you understand that X naught is taken here as 1. In our case, in our representation, we can also consider X naught is taken here. So this is your, finally, if I apply chain rule, this is your gradient value. So given any input point, specific input point, I can always compute this gradient analytically. Analytically means that this expression, I can evaluate this expression and I can get the gradient pointwise. So I do not require that kind of empirical simulation that perturb the weight and check the functional values and take the different ratios. No, we are not doing that. We are simply computing all these functional values at that point. We know the value of T, we know the value of O because I can compute this. We know the value of F prime Z because once again I can compute Z and I can have the functional form of F prime Z. We know the value of Xi because that is given as an input. So we can compute straight partial derivative of E with respect to Wi, right? So this is what the chain rule gives you. So next, as I was mentioning, I will simply just show you that given this particular interesting nonlinear function, which is a sigmoid function, and if I perform the derivatives operation, incidentally, you can follow these steps. I'm not going to describe each and every because it is very straightforward. You can do it on your own, but the result is very interesting. Result is that it can be expressed, this gradient, as the functional value of that point itself. So that means function of the functional value of that point itself. So fz into 1 minus fz. So it becomes pretty interesting. It is quite interesting to observe that. So this is one thing. Sometimes we need to compute also the gradient with respect to an input. That is also we need to compute. And there it will be simply the other thing, as you can see. And in fact, you can see there is a duality here because no, if I take the gradient of partial derivative of E with respect to Wi, let me explain this duality part. You look at this expression, you look at this expression, you can see Xi and Wi can be, can interchange while computing this partial derivative because of these relationships, So this duality exists with respect to input and the weight parameters, right? So just to rub this. Right. So that is my point, that no, the whole computations can be carried out analytically, and it can be computed at the functional value. So this is the advantage you have, and that is what we'll be using for backpropagation algorithm. And there we'll be applying the chain rule in a multi-layer network. We'll see that this can be, and the gradient value, it computes from the, as you can see, we have seen already that in the chain rule, the computation comes from the from the output towards the input side. So so that is what we have to compute there also. So from output layer towards input layer, and the compute partial derivatives of weights at the I-1th layer from the ith layer, and then you just propagate it in another way. So this is one particular concept that we need to understand if we are going to understand the backpropagation algorithm, and that is the mostly that is the essence of understanding the computations of training of an artificial neural network, mostly this algorithm, because this algorithm is so popular and so widely used. And you can see here, let me point out few things. One thing is that once again we have taken minus O whole square, as you can see, and I have just typically shown you a particular path of excitations through this neural network. So you can see that in my description, every node is numbered, and the superscript is representing the layers. So this is layer 1. This one is layer 1, this one is layer 2, this one is layer 3, and this one is layer 4. Okay, so layer so this is this is layer 1 and this is layer 2. So layer 1 means layer 1 connected nodes of this layer 1. So the input output response, you see that this layer is shown. So third neuron, first layer, then this first neuron, second layer, so in this way. And the weight connectivity also, third to first neuron of the second layer. So third neuron of the previous layer to the first neuron of the second. So this subscript shows that it is because if you give this superscript, that is the layer superscript, so it immediately interprets what should be the layer from where it is connected. It has to be the previous layer. So that's how these parameters are represented. Now the pathway of excitation, you can see, just because of this response, it is connected through this. Now this will be again will be stimulating these two neurons, and from there the responses would be accumulated and it will contribute to this output. So contribution for this response, it is flowing along this path. So when you are computing derivatives or gradient, we have to follow this path with respect to this weight. So given this weight, its contribution is felt along this path. So that is how this derivative is computed. So what we will be doing, we will be computing from here. For example, at this point, we will be computing the partial derivative of E with respect to O. Okay. Now here we will be computing the partial derivative of E. So if I say that is multiplied, so this is propagated here. Now this will be multiplied with, say, there is a nonlinear function f dash. Sorry, nonlinear function f. So let me write it as, so this will be multiplied with f dash into this. Similarly, this will be multiplied with f dash into this. Okay, and then you have to compute the corresponding derivative. So there is a weight. You can see that there has to be and weight. So this is multiplied that. So this is multiplied with so this one is delta z into this input. So if I say it is multiplied with this weight only. So because this into this is contributing. So if this weight is, say, this weight can be represented as it is W1 1 and this layer is, say, 4. So it is W114 as per our notation. So this will be multiplied by this. Similarly, again, this this is how this is multiplied this, it comes here. Again, this is multiplied by W11. Now at this point you are computing this gradient. Again, at this point, you are multiplying with this f dash with this functional blocks gradient, and you go on doing these things. But wherever there is a meeting point, like from where it is distributing, these values are going to different nodes, there you have to accumulate them. That means you have to sum them. So at this point, this contribution of gradient should be summed up, and that should be taken as the gradient at this point. So this is how this computation, the gradient computation, flows, and finally you can compute what is the gradient value at this particular point, and you can compute with respect to weight, with respect to y. That means response also, whatever is required. Okay, so this one is computed. So one of the way this computation is summarized is that at every point I am computing always, because I am always doing the computations by propagating these values and multiplying with the factor. So at any point I am accumulating what is the gradient with respect to your output or with respect to your error. So at this point I am computing, say, gradient of, say, y13 delta e delta y13, and this I am calling as delta. This is the delta. This terminology is the delta value at that point. So we have to give proper subscript and superscript notation to denote the delta uniquely at this point. Similarly, the gradient will be also propagated then delta value at this point. So it is the accumulated gradient at that point with respect to the error value. So that is what is computed. So let me just explain once again through. So this is what I have my animation will be. So as I was mentioning, I will be computing this, then I will be computing this, and it will go like this, right? It will go like this, this propagation. Some example is shown here. The same thing is shown here. So so to show that how this computation is considered, say this is the expression with this propagation. As you can see that at this point delta E delta O is the gradient at this point, and then this is the gradient. If I multiply this to this, then it is the gradient at this point, right? Then it is gradient delta y12 delta delta 31. So then it is gradient at this point. Okay, because it is delta y12, so which is again multiplied with f. So this nonlinearity block is multiplied here itself with this expression in my. So this one is computing gradient this point, and similarly this computation is gradient at this point. So these are the delta values with this multiplication of this, and if you add them, all these components are added. So up to this is the gradient value at this point. Once again, if I consider the gradient with respect to this, with respect to weight, if I multiply it, then I get the corresponding gradient value with respect to W31. That is what we need, and that is the update value for this particular weight. So that is how the back propagation is, is considered. I have some animation here also. So let me, okay, because of this drawing. Yeah. So these are the things I'm showing here. You can see that this value delta y13, delta y12. So this is y13 and this is y12, right? So in this path, what is there? This nonlinear block is there, and then this nonlinear function is there, and then the corresponding weight is there. So you are simply making product of this, right? So this has to be multiplied with the corresponding gradient value here. That is what we are explaining here. Similarly, for delta y23, so this is y23, and once again, this is y12, the same variable. So along this path, you are doing f dash z13 and w113. So this one. If I multiply this, then you get its contribution along this, and both these things should be summed up. And this is the gradient value at this point. And finally, if you want to compute this, so you have to compute gradient with respect to this and this particular parameter W31. I hope now things should be clear to you. So that is how we computed. And as I mentioned, that delta values are represented by this corresponding accumulated gradient at those points. And this is what is delta rule. There is a simplified summary of this delta rule. You can see that there are, in this diagram, I tried to explain that in the ith layer, before ith layer, you have accumulated gradient. I have shown with respect to output, but it can be also defined with respect to the error function itself. So it is the accumulated gradient value from output to this point, or from the error function to this point. And then when you are propagating this gradient at individual branch from that layer to a point to the previous layer which is connected, output to the previous layer which is connected, then first the nonlinear functions should come into the path. So you get the gradient, multiply its gradient, that is the delta component of that along that path, and then you multiply with the WKL, all those weights, right? So you get all those gradient values, delta values should be multiplied with the weights, and then that is the accumulated gradient at the kth neuron, and finally you get the corresponding weight, right? So this is how the weight updation takes place. So using this algorithm, as you can see that training of ANN becomes simpler, because what you do, you initialize the W naught. For each training sample, you have to compute the functional value in the forward pass, because you need to know all the functional values at that point. And then you can update weights of each link, because you can see, as I mentioned, analytical computations of gradient values at every point is possible, and you should continue this updation till it converges. That's the same algorithm. Some of the improvements of this particular process could be done, like as I mentioned, that when you are updating the weight or computing the gradient, and there are certain there could be some kind of outliers or noise in the data sets, or even the functional landscape may not be very smooth always. So it happens that your gradient may abruptly change. So to avoid that, we can use a running average of weights, and that we use here. So you can see that we are using the corresponding gradient of the previous iteration and taking a certain portions of it, also keeping it while estimating the gradient of these iterations. So we call it a momentum method. So is alpha is the momentum value, and this is how it is computed. And you can see here that we are computing with respect to these negations, because when you add them, it becomes positive otherwise. And there are some adaptive learning rate is also there. So this eta could be made adaptive. Increase at constant steps if error decreases, else decreases geometrically. So there are different policies of step movements. So with this, let me summarize whatever we discussed about this concept. That we have seen that the perceptron itself, it models a neuron, and artificial neural network is nothing but a network of these perceptron nodes, and it's a very powerful model. It is used for classifying linearly non-separable classes as well. And a multi-layer feed-forward network of neurons can be trained using backpropagation algorithm that also we discussed, because it is used to compute gradients with respect to the error weights, and can be used with gradients of error with respect to the weights, and can be used for regression as well. So which I have not discussed explicitly, but you understand that primarily this computation is oriented towards regression. So with this, let me stop here.